Now, in general, you can add, subtract, multiply, divide functions just like you do with numbers. That's called arithmetic. Arithmetic is the game of adding, subtracting, multiplying, dividing things. But with functions, the only problem is that they may exist on different parts of reality, which is called domain, right? As you remember, domain is the name we give for the set of all allowed x values, of all allowed, and that's the most important word, allowed, x values. Not all x values are allowed to be used, but it depends on the function. It depends on the process. For example, with the simplest possible process like x, which is a linear statement, domain is not restricted. Domain is x can be anything. You don't have to think about any potential problematic number value that you would use in your function and run to some problem because of its problematic, because of what the procedure tells you to do. In this case, anything can be multiplied by 2, no problem, XCR. Now, if I continue to complicate this function, for example, right? If I had some other function in my mind, let's say gx, which was just squaring, a square like a parabola, a quadratic function, a degree 2 function, which looks like parabola, I could have, without even naming it this way, right? Probably without doing that at all, I would just add up. I would just say, you know what, I want to create a new function. I will just add up x squared on top of that. And what I get is a slightly more complex function. Now, it's no longer a mononomial because it's not just one term, but 2 now. So at this point, we call it polynomial. But to be honest, we call anything polynomial. That looks like an addition of a couple things where things are x variables with different powers. That would be a polynomial anyway. You can add up as many things you want on top. You can create whatever polynomial function. And you can see that what I'm doing, I'm basically adding new things. And each one of these new things could have been a different function. So all of these could have been different things, right? This x squared could have been, in some other world, it could have been just an independent, a sovereign function, a sovereign process, which had a name of g of x. This x cubed could have been a guy who was also independent on his own, and he was x cubed. This guy could have been, I don't know, t of x, and he was x to the power of 5. That's what he was doing. That's what he is doing all the time. No matter what you give him, he's always doing certain things to that. They all do certain things to the input, but none of them have any restriction imposed on what values you can or cannot use. Okay. If you allow yourself to play the game of numbers where your numbers are only real numbers, or in other words, all real numbers, so if you're only playing with real numbers, which we say XER, but we say this E here, which is not really, it's not an English E, right? It's more like a in the Cyrillic alphabet, Greek alphabet. This is actually an E as the first letter for the word element. That simply means that the guy who is on the left is an element of the thing that is in the right. So X is an element of R. And what is that R? Now, because this R looks fancy, it's not just a regular way of writing R in English. It has like 2 lines here. Whenever you see 2 lines in the beginning of a letter, and it's a big capital letter, that in mathematical notation represents the name for the set of certain things. R represents the name for the set. Set means a basket, right? Some whatever, right? Some combination, some culture, some community of some things, right? So it's a community of numbers, a community of real numbers. Now, real numbers, it has nothing to do with the royal or with the reality. It's straightforward from the definition, certain definition. There are certain numbers, if you square them, they will never be less than 0. Never. So if you are one of those numbers, you are a real number. That's the definition of real numbers. If you square me, I'm an X, right? I'm somebody. I'm a member of community of some numbers. And if in my community, any one of us, upon being squared, never produces a negative answer, a negative number, if we never become negative, if we get squared, then we are a real number. These are real numbers, right? These are regular numbers. These are the numbers that you basically, we start our journey into mathematics. We start with these guys. We don't play our game of mathematics with the other communities. We start our game inside the community of real numbers. But we have other numbers, which if you square them, they actually become negative. For example, this guy who is represented with the letter I, this fancy guy I, if you square him, he actually becomes -1. So he is not a real number. He is something else. He is called an imaginary number, and that's why this little I, representing him as a kind of a basic member, very basic member of a set of imaginary numbers. Well, I said imaginary, just imaginary number. Now, imaginary numbers will have different life, but real numbers have a very certain life. If you square them, they never become less than 0. They can become 0, yes. For example, x equals 0. Yes, if you square it, it's still 0. That's fine. It's not negative. But if you take anything that is negative, like -5, and you square it, well, you get 25. You get a positive number. You see, it doesn't matter if it's negative or positive. Okay, these are the real numbers. Now, because we're playing with these guys only, it's not difficult to say whether you are having an issue with any such number using your function. Like one by one, you can say, well, if I'm just doing doubling, do I have any problem with any member of the community of real numbers? No. I can take anything I want. There will be no problem. If I square something, will I have any problem? No, I won't have. I can square whatever I want. Cube, I can cube whatever I want. Raise to the 6th power and then multiply by 3, I can do that to anything I want, to any number whatsoever. There's no problem with that. So for all of them, they all share same domain. They can all work with all real numbers. XCR. There are no restrictions. You can take X, you can take any X as an element of a real number. So basically, you can take anything from the real number set, from that community, and that will still work because it will still be part of the set of all allowed X values. Now, that means that when you add those guys together or subtract or do whatever you want with them, they all play the game on the same part of reality, which means they can all exist in community with each other. This is the second definition. This is basically the only way you can add or subtract or multiply or divide two functions is when they exist on the same, when they basically have same domain. They have to share domain. If they don't share domain, you can't really add them or subtract them. These guys all share domains, right? Now, but you can have things which are not so much using all possible numbers that have some restrictions that don't really want to use some numbers. For example, if you have division in general, if you have division and there's a variable at the bottom, for real, there must be a restriction because there's a rule, right? That
X can't be 0?
Yeah, the rule is that we don't want to divide by 0, right? Because, division by 0 is simply prohibited. I wrote this, but it's not that. Division cannot be 0, should not be 0. We shouldn't allow it to be. Division by 0 is prohibited. This is not a natural law or something. It's just we know that if we don't prohibit that, we wouldn't be able to construct a system that makes sense. So we prohibit that. And therefore, when we see situations which can potentially result in the violation of the rule or prohibition, right, then we say, okay, exclude that entity. That entity cannot be a member of this particular processing because he will destroy the system. So X, yes. And then, but you can't really, you can, but you better don't try to see this guy right away. It's sometimes not that easy to detect the guy who's going to do that, who's going to cause a problem, a destruction of the system working. In this case, it's simple. You can see, but in general, the algorithm of detecting the guy, so to detect that exclusion, to detect the potential exclusion from the domain, which is very important, because if you don't know your domain, you don't know if you can add you to somebody else. Because the only way to add you to some other function is if it's only there, you can only be added to each other only there where you share the domain, where you basically exist. When you exist on the same reality, on the same portion of reality, then of course you can communicate. But if you don't share the same background of domain, you can't communicate. There's no way you can add or subtract, even though it may look like you can, but you still cannot by the rule.
Right.
So for this purpose, you need to know the domains. And for that purpose, you need to know potential troublemakers. And to know that, you need to know what trouble is. And to know what trouble is, you already know that. You know that trouble in arithmetics is division by 0. That's one set of troubles. To detect the potential exclusion, we have to do first to investigate potential troubles. And there are two kinds of potential troubles with real numbers. It's division by 0, or it's a negative number inside of an even radical. To investigate two potential circumstances. Now, division by 0, okay, you got that. That's one, division by 0. And the other one is negative, the guy who is inside the radical. But I have to be negative radical inside in a in an even radical. With these two situations. So division by zero is prohibited, and also because negative number inside this thing, whoever that thing is inside there, if this degree is inside an even degree thing like that, radical, cannot be. Also is prohibited. It's prohibited because of the definition of a real number, which is, as we said before, which is if you square a real number, they must be positive or zero at least, but no less than zero. They can't become negative, which means that if you ever try to go backwards from that result upon squaring somebody back to what he was before he got squared, or raised to the fourth power because it just keeps squaring, or sixth power, it still just keeps squaring, right? Or squaring and multiplying by another square. There is no way the result of you doing those squarings should be negative because it's prohibited by the very definition of what real number is. If this ends up being negative, then this thing you were using, the number you had in the beginning, before you square him, he wasn't the real number, he was something else. He was probably an imaginary number. But we're not using imaginary numbers. So there's no way this can be negative. This must be non-negative. The only way the inside of an even degree radical can be negative is if you are allowed to use complex numbers, which complex numbers is combination of real numbers and imaginary numbers. When you're allowed to use both real and imaginary, then you call it a complex plane. It's the more complex reality. It's a bigger community of entities we can use. When we use that community, we can solve bigger problems. We can solve much more problems, many more problems. We can solve problems of statistics, problems of quantum mechanics. But here at this point, we're dealing with this. So we have to remember these two obstacles, two potential problems. And then basically, when you know that, that's it. That's the fundament, that's the framework. Everything else is within that framework, right? Just make sure you search for potential troublemakers, knowing what troubles can be. Now, for example, if I give you radicals, two functions which are, I don't know, maybe one is radical, another one is non-radical, another one is a regular polynomial. So I don't know, maybe some quadratic polynomial with a positive a value, so 2 times x squared, whatever, minus 3x plus 4, for example. That's a very regular quadratic polynomial. Okay. Now, his domain, he got no problem in the community of real numbers. He can process any entry. He can process any member. So his domain is not restricted. His domain is everything, XER. All elements of real number set can play the role of an X. Anybody can become an input, any real number. But here, you know that the moment first of all, if I don't put anything here, I mean 2. But it doesn't matter, right? It only matters whether it's an even or odd. If I put an odd thing here, that will be very different. But let me put 4 here first. That's 1. And let me create another function, f, g, and h. And for the h, I'm going to actually put there 3. I'm going to make it an odd degree radical. And that will change a lot because although here it makes difference what's the radicand, because you can't, neglect the prohibition of not having anything negative inside an even degree radical. But for the odd degree radical, such prohibition does not exist because raising somebody to an odd degree, cube, 5, 7, allows you to have a negative result if you were a negative number in the first place. If you were -1 in the first place, of course, every time you're raising your -1 to an odd degree, you will still get the negative answer, -1. Whoa. It will be for 3, it will be for 5, for 7, for any, because an odd number in an exponent is not just a fancy number standing on top of the world. It has to stand there because we define that place to bear a certain meaning, and that meaning is the number of times the multiplication by this guy happened on top of number 1. This number position represents a certain meaning, which is, in an English language, the number of times or the number of multiplications something got multiplied, right? It's the number of multiplications that, well, that's the number of multiplications of whom? Of -1, of the base number, whoever that guy is, on top. Multiplication should happen on top of something, right? You have to multiply on top of something. You have to have something there waiting on top of number 1. That's the definition of it. And because Doing that once will give you -1. Doing it 3 times will still give you -1. Doing that 5 times will still give you -1. And if you change the number to -2, okay, yeah, I mean the magnitude of the number will change, but the minusness will not change. The negation, the negativity of the result will still be same negativity, because the negativity of the input repeated 3, 5, 7, 9 times, odd number of times, still ends up being negative, because negative sign multiplied odd number of times still produces negative results. That's just a fundamental, so to say, double negation of logic. Double negation means positive answer, right? Triple negation means it's just logic. That's just the way. Fundamental ways of discerning reality or dissecting reality for our languages. It's mostly for Western languages that are binary. That's the fundamental basis of binaries, disposition of reality, let's say. Okay, so now these are the conditions that must be set. This guy, therefore, being inside an odd degree radical, he has no problem whatsoever. He can be whatever he wants. He can be negative, he can be positive, he can be 0. He has no restrictions to his essence. So I can write whatever I want here. Let's say 3x squared minus 4x. Some weird. It's also a polynomial, also degree 2. Okay, also a quadratic function inside a radical. And now we can say what are the domains of these two also. And we already said what's the domain of this guy. So let's say what's the domain of this one and what's the domain of this guy, so that we can know if we can actually play together, if we can actually use them, use maybe 2 out of 3, maybe all 3 of them to create some other function, to combine, to have a composition, to produce some combination of them, something more complex, perhaps, maybe not complex. But in order to produce that, in order to allow ourselves to actually add or subtract or multiply or divide, all of those possible, all of those actions can only be done if, and it can be g of x, can be h of x, whatever your combination you're trying to create. It only happens on shared domains, only happens on shared portions of their domains. Shared portions. You must figure out what are the domains of each one of the entities who are about to play this game, and then you have to see whether those domains actually intersect, overlap. Shared portions, you can say overlapped. That's another way of saying it. Or you can say intersection. If you think in terms of sets, you can always say, oh, intersection of 2 sets of things is what is shared between both things. And that we call an intersection. And we have a beautiful letter that represents it, because intersection means it exists in both realities. If you call this reality A and this reality B, then this is an intersection of A and B. This is just A, this is just B, but this is not just B, but also A, right? So that would be A intersection, but intersection we represent by the letter A. And we don't write it like A, we just write it as a little roof. And that means and. It's like a signifier of the letter A, old version of the letter A. And that means that both A and B are true in there, and symbol, in other words, means intersection. It's synonym.
What's the
intersection for?
What's the difference between that and the union symbol?
The union is when you don't care about, when you are not so strict in your choice. And is when, right, in logic, in English language, when you say and, you mean both.
Yeah.
And means both. But when you say or doesn't necessarily mean both, right? Like if you go to a cafe and you ask, I want to either, fried chicken or something else, or a salad. Well, it's like if they say that we have both, that wouldn't be a problem for you, right? That's fine. You're okay with both, with each, right? Either, right? Either means I don't care, whichever one. So or is a situation where you actually don't care whether you have both or whether you have only one out of 2. That's or. Or is bigger than and. And strictly means I just want that thing that is both this and that. Okay. But when you say or, you say, no, I don't care. I can have just the B. I can have just the A. I can have the thing that is both A and B. I don't care. Actually, the more the better, in fact, in most cases. Right? So not always, of course. Sometimes less the better. So this is, so the green, I would say, you know what? This is actually a union. And you kind of feel, right? Because union means everything together, right? Yeah. Not just that. So that's the difference, right? Union is or. And this is like O. It's kind of O. I mean, I know. I remember this one. Actually, we do draw those symbols either in a fancy circular way, more oriental, or we draw them more Western with a little bit more angle, more right angle. So it either looks like that or it looks like this. So it's like either it's curvy or it's not curvy. But the direction of the opening is what matters. This guy looks like A, it represents A, so it represents intersection, overlap. This guy looks like U, so he represents union, and that's OR. Union, or in other words, OR. And it's not strict, it's not a strict OR. Sometimes we have to say we mean a strict OR. When we mean a strict OR, we mean either that or this, don't give me both. That's a different one. That's not a regular OR, that's a strict OR. If you have to use a strict OR, the people who work with, who actually trying to tell you that, will have to show you this particular symbol. Strict OR doesn't look like this. Strict OR looks like this, which is also a sign of perpendicularity. Two lines being perpendicular to each other, right angle. And right angle in logic means things that are independent of each other. Things that are coming to each other at right angles, we call them orthogonal. Ortho means right. Gonal means sided. Orthogonal, right-sided. Ortho, this, when you try to make your teeth right, it's also, the word also starts with ortho. Ortho means right. Right angle, right-sided means, in other words, perpendicular in more English, more Latin. This is Greek, perpendicular. And in algebra, perpendicularity happens only when two things are independent of each other. And because we're talking about lines, we say it's linear independence. And linear independence means what happens in one thing doesn't affect the other guy. Basically, they're independent of each other. They don't affect each other. And that means strict difference between one or the other choice. I don't want to have a choice that incorporates both of them, because if it incorporates both of them, they will clearly affect each other, right? If you're choosing a part that is both salad and fried chicken, that's like, first of all, it's weird, and second, it's like if they both can be that, if something can be both a chicken and a fried salad, which is a bad example, right? Let's say, I don't know, if something can be both rice, I don't know, maybe both a certain kind of a leaf and a certain kind of a flower, it kind of intersects. They might be same, they might not be same, they might have this communication, they may not have. So they may affect each other's existence or they may not. It's not that strict. That would be just regular OR. Now, you're not going to use that too much. In university, you will see this. This becomes very, very important to have strict OR. But at this point, OR is union. Everything, non-strict. Both and separate. Okay, now, for our purposes, we can't use OR. We need to use AND. We need to talk about shared portions. We need to talk about those segments of domains that are utilized by every single function that we are trying to incorporate into a bigger function. There's no way you can put two things together if those two things are they're not basically sharing the same, well, I don't want to say background, right? But they share the same domain. Domain is where the function actually exists, right? Domain is where the function can produce a value, where it can do its job. If something is external to the domain of a function, then function cannot do anything at that particular position. It cannot really process that entity, that input, that value. Now, for this guy, there's no such problem. He can process anything. Whatever you give him, he will produce an answer, which will be part of the range of his action. When elements of domain get processed through a function, when function actually eats them, you can think about function as a fabric or a factory or an organ, any organ. Let's say a stomach. You give a stomach food, right, through your mouth, and stomach eventually gets it, and then it does its job, right? It utilizes a whole bunch of other things, of course, but it creates something. It basically breaks down the chemicals, the molecular structure, releases certain kinds of energy, then sends it to the blood, and then some of it gets sent to gets into your, access to the blood, to all parts of your body, to every single part of your body. So there's a functioning process going on. And functioning process of a stomach is taking certain inputs. Of course, he has his own domain. Not everything you will give your stomach will actually do the job. Only those things that are part of the domain of the functioning stomach process will actually do something, will actually be utilized. But then eventually, after they're being utilized and processed, you get the results. Whatever those energy chemicals you get into your body, right, released after this process. That will be the range. So that will be Y. That will be the set of all possible answers. And in this case, we don't know exactly what the range is. It might have some limitation. It might be limited. So we may say this is the range of answers. There's actually another name for that, an image. And it's more precise. But again, at this level, grade 12, you don't need to know the difference. For now, we can just call it range. The range of all output values, of all outputs, of all results, of all consequences, depending on how you want to think about a process depicted as a function. Now, clearly, because this guy is a parabola, he will have some limitation. And because he opens up with the number that is greater than, we call him A. This is A, right? This whole thing is B. This whole thing is, what defines the direction of a parabola is A.
Right.
And there are only two possibilities, right? Either it's bigger than 0 or it's negative, or it's less than 0. If it's bigger than 0, it tells you that your parabola you're about to draw will be opening up. Now, it's probably not going to be passing through the origin or whatever. I don't know where it's going to have its vertex or whether it's going where it's going to have its x-intercept, because for that we need to actually find them. I don't care. I just want to show you the fact that if you have a parabola that is opening up, then you're definitely going to have in your range, then this guy definitely going to be in his answers produced, he will be bound. At certain position, there will be no lower answers to be produced. He will have an absolute minimum of results he can give you. So he will have a certain limitation on his range. His range will be basically bigger or equal to some particular position. And that position will be the vertex, of course. And that will be, and you're not going to use the whole vertex, all of the coordinates, right? You're not going to use both of the coordinates for your range. You will only use the coordinate of the answer, which is y coordinate. So you'll say, oh, my range, in this case, the range of this guy will be, I don't know, greater than something, greater or equal to something, whatever that something is. We can actually find that. Actually, there's a way of finding it. Like, if you want to say that, oh, my range is going to be bigger or equal, at least equal to the very bottom part of my parabola, which happens to be the vertex by definition. So I just say vertex. But I can't say vertex. I have to say vertex's y coordinate, because it's not the whole point that I'm talking about. I'm talking about the altitude, the result, the smallest result I will get. Here it's going to be the smallest one. If A was, on the other hand, negative, now it will change my range. Now I will have to expect a range that will have an absolute maximum instead, because now my parabola is starting with a negative number, which means it's going to be opening down, which means there will be a top instead. Naturally, it has to be the top. If you're opening down, you have a top. So then the result you're going to expect will have a certain different kind of limitation. Now there will be a level above which your graph will never exist. So when you say that in English, when you actually write down that range, actually it's not English, it's more like set notation. You say, well, it might be now what? The green thing, so this was red function, G. And let's say this next one would be a potential range description of a green version. Also G, whatever. G of X, I mean. So, well, in this case, it will be in the green case, and Y values will always be less or at most equal to a certain value, which will, again, be, of course, by definition, a vertex's Y coordinate. But we know that vertex's Y coordinate has a label, and it's labeled as K. If you remember that, right?
Right.
In the vertex form, it was HK. That was the vertex, by definition, right?
Mm-hmm.
So now, and there's actually a way of finding the vertex, a very fast way of finding a vertex, which is something you can understand if you look at the quadratic formula a little bit more focused. If you think about what it means, you can justify to yourself that the vertex is a position that is equal to, that is produced or achieved or understood, calculated, figured out somehow by doing minus b over 2a. And when you do just minus b over 2a portion of your quadratic function, you understand that you are at the middle. That becomes the h value, the very x-coordinate of your vertex. This is what the vertex location. How the vertex location can be found very easily without completing the square. Does that make sense how you get that one?
Yeah.
In the middle, right?
Yeah.
Okay, so this is this. Now, that allows you then to find the k, because you can just plug in your k into your function. That will give you the k, right? You already have your function. That's your function. You've got the x-coordinate of the vertex, plug that h value into your function, allow it to be an entity that will be processed. He will be processed, and he will become something else at the end of the game. Something else will be the answer, that will be the y, and that will be the top or the bottom. So now that's the range. In regards to the domain, we have to find the commonalities. Now, commonality between these, the G and F, might not be that big, because F is a radical of an even degree. And we know inside an even degree radical, nobody can be negative. So we have to restrict that possibility from our game. We have to tell ourselves that, look, we can't have that happen. right? For this guy, I have to say, let me rewrite him here again. For f of x, saying this, for him, if this is the case, then the inside, the 2x plus 1, should be, it has to be, at least equal to 0, but of course never less than that. It can be either bigger than 0 or it can be at least equal to 0, greater or equal to 0. It cannot be negative. Should be non-negative. If you set that inequality to yourself, you can then figure out what x should be. You say, well, if 2x plus 1 should be this, and you know that the game of inequality is the same game as the game of equality. You can move around things. You can do everything as you did before with equality. The only difference is that if you ever have to multiply or divide any side of inequality by a negative number, then you actually have to change the value of the inequality to the opposite one. So for example, if I have to multiply the left side by a negative number, by a negative 1, and make it like negative 2x minus 1, right? If I multiply both sides by a negative 1,
right.
I have to multiply the right side by a negative 1, but in this case, 0 will not change. It will still be 0, but the sign will change.
It flips.
Yeah, it will also get negated. It will also flip to the opposite version of himself. Exactly. So that's the only difference. That's the only extra thing about inequality if compared to equality. Right. Now, but then finding this inequality, then you can solve that inequality, which means you can find out the limitation on the x values, on the inputs you can use. So you say, oh, that's it. Okay, so 2x bigger than or equal to plus 1 goes there, becomes negative 1. Okay. Divide both sides by 2, x bigger or equal to minus 1 over 2. So my x should be at least minus 1 over 2, or minus 0.5. It should be not less than that, this or bigger than that. So that's the limitation on this guy. If this is the case, then 2x will be greater or equal to minus 1, and 2x plus 1 will be greater or equal to 0, right? If 2x is greater than minus 1, then minus 1 plus 1 will be greater than 0, right? So it's the same thing, right? In math, both directions are same. If you can go from here to here and from here to here, that means you can go from here to here and from here to here. This is called deductive reasoning. In deductive reasoning, you can go backwards. In inductive reasoning, you can only go one direction. Inductive reasoning is what we use when we work with empirical data, which is data that comes from senses, perception, all life situations, all natural sciences, biology, chemistry, psychology, anything. Deduction is what we use in mathematics or formal games, where it's not what we experience that matters, it's the rules that we actually preset beforehand, which what matters. It's a formalized system. It's like a form. It's not a thing. It's a form. Okay, so that's the difference. Okay, now you got the domain of this guy. So this is not just x bigger. It's not just a solution to an inequality. It's a solution to an inequality that had a very important meaning in his context. Context defines the meaning. The context of this inequality is not just inequality. It's the definition of the domain. This is the domain for this guy. That's his domain. Then this thing is mean, which therefore means that its domain is this. So now this is the portion of input reality, horizontally depicted as an x-axis, right? Which you can use to work with this guy, with this function. Must be minus 1 over 2. Yes, it's a dot that is filled up with ink. Anything to its right side will be useful. Anything that's to its left side cannot be used. Impossible. So that's his reality of existence. Now, what about the reality of the other guy who we're trying to combine him with? And we actually didn't really try to combine anybody with anybody else, but we can write it down. We can say now. We can actually now ask those questions. We can say, okay, can I actually add those two things? Can we add let me take that away. Can we add f of x and g of x? What do you think? And if yes, then where exactly?
I think we can.
We can, for as long as what? For as long as they are on the same ground.
In the same
same reality. The same portion of reality. So they actually can exist there. Both. Now this guy can exist everywhere, right? Yeah. See, this guy doesn't care, XCR. But this guy cannot exist everywhere. He can only exist when x is bigger than or equal to minus 1 over 2, right?
Yeah.
So what is the overlap between the two domains?
Like where can they be to? So okay. So only in like positive regions or like real numbers above 0 or above -1/2.
Yeah, exactly, right? Don't just guess, right? This guy screams at you, tells you like, look, I cannot exist if you give me anything less than -1/2.
Okay.
He's defined there. That's his domain. Yeah. So and that's the shared. Of course, he is more limited, right? When you have something more limited with something that is less limited, of course, it's the more limited that is going to produce the shared answer, right? Because he's more precise, let's say. Okay, so yes. So if the question is, first question, if the question is what is f of x plus g of x, the answer would be obviously just adding those two things. Fourth degree root of 2x plus 1 plus all of this, 2x squared minus 3x plus 4. Of course, it could have been subtracting, and then you would have subtraction here. Nothing will be different. And I mean, of course, appearance eventually will be different. We'll be subtracting the whole thing. I should put the brackets here because that subtraction will change all the other signs. So yeah, but in terms of domain, nothing has changed. So what's the domain for this guy? So if I ever ask you what's the domain of, and there's actually, well, yeah, let's just write like that. F plus g. That's another way of writing it. A more short way. Instead of writing fx plus gx or fx minus gx, we can just say f plus g and write x only once, right? Instead of twice.
Okay.
That's a little bit more like less space consuming. Okay. And you can do the same thing with the multiplication, division, and even with the composition, which is when you put one function inside the other function. And you see that little empty dot that looks like a little O or a little zero. That's another one. That's the highest level of composition, the most complex way of composing things. This is the least complex way. This is adding, just subtracting, just multiplying, just dividing. Very simple arithmetics, nothing special. But the domain of the result of doing those things is exactly what we found, the shared portion of the domains of all entities you use to create your composition. So whoever is being used, whatever function is being used in your composition, you have to figure out the domain of each one of those. And then you have to compare all those domains and figure out what is the commonality, what is the overlap between them, what's the shared region. Exactly. So if it's 25 functions, you have to find domains of 25 functions, and you have to figure out what portion is shared by each one of them, right? Because if they don't exist, again, if they don't exist somewhere, how can they be there? It's like, by definition, right? It doesn't exist there. It can't be there. Now, in this case, the domain of these two are, what is it? Well, we found it is x greater or equal to -1/2. That's it. That's their shared domain. Now, if you use this guy, that will be simpler because this guy actually has no restriction whatsoever. And you can tell me, Ayana, why is this guy not having any restrictions on his domain?
He has an odd degree, so
anything
you multiply with, or if you, I think the definition was if
number of times you multiply something on top of number one.
Yeah, that was the number of times, yes.
However many times you multiply something on top of one.
Yes.
Right? That is basically a number of multiplication. Remember, exponent means, by definition, a repeating multiplication. A repeating multiplication, in other words, is called an exponent.
Right.
Well, after multiplication, should say an exponentiation, being proper sense. Exponentiation. What? Exponentiation. Yeah. But we have to understand where, again, right? What are we multiplying on? On void, on zero, on emptiness, on me, on what? On number 25? No, on number one. Number one is always there. For the purposes of multiplication, number one is the beginning of the game. So then if you multiply number one by 3 twice, when you multiply by 3 once, you can actually say, you can call it, in terms of a repeated multiplication's other appearance, which is an exponentiation, appearance with an exponent. You would say, I am using 3 as my basis, as a base number for multiplication, as a factor, as a multiplier, as an operator of multiplication. 3 is operating the multiplication. Without 3, here, there will be no multiplication. He's an operator of that particular action. He is operating on top of 1, and he only happened once, so that's 1. That place in the exponent will be populated by number 1, and so on. So at this point, it would be actually 3 happening twice on top of 1 through the act of multiplication. And that would be a simple way of writing multiplication. And that's what you were trying to say here. So if you can say it again, can you say it again in more appropriate terms?
So the reason that this doesn't have a limitation on the domain is because it is the multiplication of any number by 1.
Odd number of times.
Wait, sorry? Is that at the end of
you said it's a multiplication of any number on top of 1, but it's a multiplication odd number of times, right? How many times are you going to multiply a number on top of 1? Odd number, 3 times in fact, right?
Right, like the number in the index.
Yeah.
The amount is
index represents however many times that multiplication should have happened in the past to give you what you have right now, right?
Yeah.
So somebody was taken, we don't know who that guy is. He was taken and used as a multiplier, as an operator of multiplication on top of ever weighting number 1 in the beginning of the game. And he actually happened 3 times in a row. And he eventually, by doing this, produced what we have right now.
Okay.
This thing, whatever that is, 3x squared minus 4x. Now, but because it happened 3 times, we know that he could have been negative and he could have been positive. It doesn't matter. It's okay, right?
Right.
And if he was negative, or he could have been negative or positive anyways. But the problem is that if he was negative or if he was positive, doesn't matter. If he happened only even number of times, 2 or maybe again, then the thing that he produced eventually will have to be positive or 0, but never negative, right? Because real numbers being multiplied on top of each other in an even number of times can never produce a negative answer. But because this is to degree 3, it happened only 3 times, as you said, which means he could have produced a negative answer as well. He could have been a negative guy himself, and that would have resulted in a negative answer. Yes, and a negative consequence, a negative output. Yes, so that can be negative too. So there's no restriction on this guy. He can be negative, he can be positive. Obviously, he can be positive because he's just real numbers can always be positive. He can be 0 because real numbers can also be 0. He can be negative because the degree allows him to be negative. Okay, he can be anything, XCR. This guy has no problem. You can plug whatever real number you want. You will always get an answer. And that answer will always be well defined. It's not going to be like 0 divided by 0 or something, right? I mean, there's no division here anyway, right? So you wouldn't need to use the idea of a limit to figure out a way of approach to a state that is discontinuous. You were asking something.
I was going to ask, it was kind of like a side note. It's just because we've been discussing radicals with variables in them, and I was wondering if I ever happened to see that in terms of a question and I needed to solve it. How would you, I don't know if you can solve it, but how would you simplify
What question? What kind of question?
Like if it asked me to find the value of x and it was written, for example, in the form of h of x. Like on that, in the radical.
What is written in the radical?
Like
what
x,
are we trying to find?
X.
But we will not know nobody what kind of an x. You have to know, first of all, there is no question. There's no answer to be found unless there's a question. Just saying find something is not a question. You have to give a condition.
Okay.
Whether something becomes an answer or not depends on a condition set. What is the condition? Like if you ask me, find a 0 to this graph of this function, that's very, very, very particular condition. I will know what I have to do. I will equate the whole thing to 0 and then try to find the x values that produce that answer potentially, right? That allow that condition to be satisfied, right? You have to satisfy a condition. So again, tell me what condition you are looking for. You can ask me many things, right? You can ask me what's the domain, what's the range of this function? Does the range of this function has any limitations? Is there a maximum? Is there a minimum? Or is there none, right? You can ask me, does this function's graph ever touch the ground? Which means, can there be the case where the whole thing equals to 0, being on the ground, right? Find the x-intercepts. Or you can ask me, can this guy ever touch the y-axis? Which means I have to set x equal to 0 because y is where x is 0.
Okay, how about the zeros? Let's just try to find the zeros. I think that's the most likely.
Oh, okay. Yes, so for radical, right, you mean? You want to talk about radical specifically? Yes. Well, it's the same thing, right? Now, so a condition of 0 implies, right, there's an implication, right? Again, because it's deductive reasoning we're using here, you don't have to worry about implications. If it's implied, it's implied. Both ways are true. Again, it's not something that's a sensory thing. A condition means there's an implication. A condition of a for the zeros, potentially, maybe there's one, maybe there's many, depending on the degree, of course, for the zeros, implies the act on your behalf of equating the whole thing to zero, equating the whole function, the entire expression, the whole functional expression to zero. That's what it implies. You have to do that.
Right.
That particular act must be done. Otherwise, you wouldn't be able to find anything. I mean, you can, of course, just by looking, if it's simple enough or whatever, or you can see it. But in this case, I will just do the regular thing. I would say, okay, I'm going to equate the whole thing to zero, which means this particular thing, right? Which is x squared minus 4x, degree 3 radicand, equal to zero. And then I will look at it and I will say, well, there are a couple of ways of dealing with it. I just have to think a little bit. I have to ask myself, if this whole thing, a radical, is actually producing zero, then what should be produced inside of him? Radicand, in other words. What should the radicand be equal to? How 0, 2, right? 0, 2. So you basically can just see it, right? But it makes sense. Or you can justify it by doing algebra. You can say, well, you know what? I want to release him from the cubic function, from the cubic radical, and I know how to do that. I will just have to cube the whole thing, right? If I raise the whole thing to a cube, to the third power,
right.
And of course I have to do the same thing to the right side, I will release this radicand inside, outside, into the outside of his original whatever environment. He will no longer be inside the radical, he will now be outside of it. He will just look like 3x squared minus 4x on his own. And the right side will still be zero. It'll still be zero. 0 raised to any power is zero. Perfect. Zero is a good thing. It's a good number.
Right.
Okay, and now it's a very simple situation. Now, what you have to remember is always the fact that zero as an idea is equal in its definition, in its meaning, to the idea of a root, but it's also equal to the idea of a number inside a factor. Right? A factor, and that number, a factor is always x minus some number, and I'll call it, let's say, just r, root. So whoever that number is, root, he is the root. He is the zero. The root of the zero. There's another name for it, for them, x-intercepts.
Right.
Places on a graph that actually get in touch with the x-axis. But because x-axis is a ground, and it's called the ground because it's horizontal, and because we walk on a horizontal surface, humans, we can call it ground level. And it's a ground level because it's a zero altitude. X-axis happens exactly at the halfway in, right in the middle of the y-axis, of the wall, the great wall here, y-axis. Y-axis happens at the middle of the x. X happens at the middle of the y. That means that when you want to find anything that is lying on the x-axis, literally you have to do only one thing. Because there's only one thing that is true about any one such position, and that is the fact that they all have the same altitude, namely the altitude of zero, right? Because they are all lying on the ground, and the ground is defined to be the zero level, ground level, whatever, the water level, the sea level, the ground level, the zero altitude. That's what's true about anything on the x-axis, which means if there is any x-intercept potentially, all you want to do is equate your graph to zero, because if it is possible to make it equal to zero, it means it must have been those very x values that did it, right? That correspond to it, that produce that answer, which justifies visually the reasoning behind setting the whole function equal to zero in order to start your search for the zeros. It's the same thing, tautology. It's all circular, it's the same thing. You can see it visually, and then you can say, oh, that makes sense, verbally, or you can maybe understand verbally better and then kind of see a picture, or you can actually just like algebra and get things algebraically first and then use the help of a picture and the formal statement that describes it in English language. Actually, it's a natural statement, that's a formal, that's a pictorial, visual interpretation, formal and natural language. You have to try at least to have 2 out of 3 so that your life is easier, because it's good when you have many ways of describing the same thing. Okay, so yeah, now here what's important is the most important thing about roots. first most important thing, yes, of course, is that the whole thing must be equal to 0. The function must be equal to 0. But the second thing, which is important in order to find them, do the proper process, is that you have to search for the factors. Because if you can find the factors, by the very definition of what factors do, you already found the roots. Right? It's a factor theorem. One of the fundamental theorems tells you that.
I remember that.
In order for a portion of a function, any statement, whatever the statement, whatever the process, whatever the architecture, maybe it's an organism, maybe it's whatever, in order for a certain portion of that big thing to be called a factor of it, an X factor, whatever factor, main factor, not important factor, crucial factor, whatever, but to be a factor of something, it's not just that you have to be connectable to the whole through multiplication. That's one thing. But in order for you to be connectable through multiplication to the whole thing, you yourself must contain something very crucial in your structure, on your level, in your smaller structure. And that crucial thing that you contain in order to be counted as a factor is the root value. You cannot be a factor of something if within you there is not a root value. One of the roots of the whole process that grounds that process to a certain reality, to a domain of that process. If you don't have a grounding in the domain of the process, it means you're not connected with the ground. You're basically not connected with that realm that allows you to exist. That's important on all levels of science. Finding factors, therefore, is equivalent to finding roots. And it's simple. It's just pure algebra. You try to, what is a factor? How can a factor be found? By extracting a commonality, searching for commonality. You say, well, what is the extracting? Maybe sounds a little bit too much. By extracting, I mean simply placing things in two different positions. So 3x squared minus 4x. Is there anything common about these two things? Yes, of course, right? X. X is common. X can be factored out, not extracted. Factored out. He's already a factor. You factored him out.
Yeah.
What's left is 3x minus 4. That's it. And now the equality to 0 can be approached in a more, how would you say that? In a more detailed fashion. It's like, instead of having this equal to 0, now you see that this guy can be equal to 0 and this guy can be equal to 0. Both of them, each one of them can be equal to 0. And it's enough for each one of them to be equal to 0. If this guy equals to 0, the whole thing will have to be equal to 0 as well. Because when you multiply somebody by 0, you still get 0. Of course, unless the other guy is infinity, but the other guy is not going to be infinity in most of the cases. And you can see it. Well, it's not going to be infinity. 0 minus 4 is minus 4. That's not infinity. So 0 times something is going to be 0. Him being 0 produces one root. And you can actually see him as x minus r, where r is 0. You can literally see that if you write this guy as x minus 0, you can just see x if you wish to. That 0 is hiding, so 0 is the root. So if you plug in 0 here, he will get 0 minus 0, he will become 0. He'll produce the 0. And for this part will give you what? What's the second root value here?
It's going to give you 3 over, or 4 over 3?
Yes, you have to destroy 3, make 1 out of it, which means division by 3. And then you have to take that number 1 and recreate number 4 out of it, which means multiply 1 by 4, which means put 4 on top. Right?
Right.
Have you ever thought like that about numbers?
No, I haven't. The way you explain them is interesting.
This is a little bit different way of thinking about it, but that's kind of a natural way of thinking. That's the initial way of thinking about it. Right? Every number is an action. You know it, right? You just never say it like that, but you know it. It's an action, right? It's an action, and you know what actions are there inside the number, because you know that the top part of a number, since you can work with rational numbers, and a rational number simply means a ratio, and the rational number is a very common member of a real number reality, right? Many numbers are rational numbers. So you know what the rational number is, and you know it must have a top and the bottom, and you know that the top means multiplication, and you know the bottom means division. You know it implicitly. You maybe never heard it explicitly up until now, but implicitly in all your actions before, whenever you had to multiply two rational numbers, you always use that implicit knowledge. You always did cancellation in a proper way. You would cancel this 3 with that thing, right? You wouldn't cancel this with that. Why would you cancel this and that?
Because they're opposite operations.
Because they're at opposite positions. One is on top, one is at the bottom. And because the bottom exactly to the top means an opposite operation. And more specifically even, the top means multiplication, the bottom means division.
Right.
right?
Yeah.
The place, the bottom. Remember, I told you many times, the spots. What matters in mathematics is the meaning behind the spots. The numbers themselves can change. But yeah, division, yes. So it's there, right? So okay, so that will be the other root. And what we will do with that root? We will find it. We already found the root. You will say that yeah, there are two roots to this function. This function will touch the ground at 0, and it will touch the ground at 4/3.
Okay.
That's the way to find the solutions. Actually, that's another name, right? The final name is, but this name is a little bit weird because we call it the solution. But when you say the solution, of course, you need to know the solution to what? To what problem? The solution to what problem? And when we say the solution, we simply mean, we just mean it's the solution to the problem of finding roots, of finding zeros, of finding x-intercepts, of setting your whole thing equal to 0.
Right.
The solution, right? But of course, the solution can be to anything, right? If you equate this thing to, now, for example, if you equate this thing to 2, that will be a little bit different. If you have time for that.
Yeah, I have time for that.
So if we create this instead, if we create a little bit of an exponential type of equality to solve, 3x squared minus 4, the same thing here, cubic root, degree 3 radical, this is 4, equals to 2 now. So let's say this was a situation you were dealt with for some reason. I don't know what the reason is behind it, but it was given like that. Now, clearly, the question is now not to find the zeros, right? First of all, nobody set this equality to 0. And second, nobody asked you to find the solutions. But if they asked you to find the solutions, they wouldn't give you it like that. They would actually put this guy on the left side, right? He will be on the left side. He'll be here like -2. And then the whole thing will be called some name. I don't know, h of x, let's say. And then they will say, can you please find the x-intercepts for this guy, if there are any? And you will do the same thing, right? You will equate the whole thing to 0. You will move this guy to the other side. It will mean that this guy must be, of course, +2. And by the way, this is the regular way of teaching it. But of course, if you think about it naturally, to have this side produce 0, be equal to 0, means, well, you're subtracting 2 from somebody and you're getting 0. Well, obviously that something must be 2, right?
Oh,
How else can he be?
yeah.
Obviously, right? Just because you know how to operate like a machine doesn't mean that you don't understand what's behind. That's an important thing to remember. Just because we can be mechanized and do many things automatically, it doesn't mean that we do not know what we're talking about. And it also doesn't necessarily mean that you know what you're talking about if you do something mechanically. Both. Okay, but we know both most of the time. So that's not the question, though. I don't want to ask this question. I want to ask a question. I want to actually equate the things and see if we can actually solve that problem, which means it's a different kind of a problem, and it means it requires a different kind of a solution, but the same tactic, same method. It's just algebra. There's nothing else we can do about it. Just play around with two sides of an equality, do things correspondingly, do whatever you think is right to both sides always, and you'll be lucky. You will get your hands on the thing that you're trying to find. You will find it. So in this case, what would we do? How would we get closer to the?
Wait, do we take the cube root of 2?
Well, if you take the cube root of 2, then you remember you have to do the same thing. You have to do the same thing on both sides of your equation. Any equation. You can't do just both, right? So would you like to do that?
No.
What?
Maybe.
That's too much. Are you saying you would like to cube instead?
Yeah.
Exactly. You want to liberate. Remember, it's not the 2 that you're looking for. 2 is already looking at you. It's already staring at you. It's not hiding anything. It's just a number 2. It's the x to solve this, so I have to take away this. If somebody tells you to solve this, nobody even has to tell you that, to be honest, explicitly. Because if a left side is set to the right side, and there is something inside the left side or the right side or both sides that is not known, then the thing that you can do, the thing that you may do, the only thing you can do actually is to try to find the unknown thing. To solve means to solve for the unknowns. That's what it means. Whoever is the unknown. Well, the unknown here is just x. Yes, it happens to degree 2. Yes, it happens actually inside a polynomial and actually inside a radical of degree 3. So he's quite hidden away from the surface. He's like 2 or 3 levels below. So it's like archaeology. You have to excavate the thing. Algebra is also an archaeology. You have to excavate what you want from what it is, from where it is. But the only difference is that you have to do whatever you're doing here, you have to write down the same thing on the other side. And that is what accounting is. You have to account for your actions. Whatever you do on one side, you have to do the same thing on the right side. And eventually, everything that you've done to the left side to excavate the thing that you wanted to find will be written down the same way, exactly the same way, on the right side. And that right side will eventually be the very answer you wanted to have.
Right.
Because there will be nothing left on the left side to find. It's basically a transition of, it's like translating the actions to the answer. Yeah, your actions become a replica of an answer. You're kind of building your answer. It's different from sculpting in that way. It's actually building an answer. But you're doing archaeology by building. It's like you are digging deeper into soil, and then you're taking the soil, and then you're actually creating something else on the other side. You're creating some structure, something that's like using potential and creating an actual thing, like balancing. So let's do that here. But we have to do, of course, we have to know what we want to get, which means we also need to know how to get there. Like we need to know what to use to get. I just said cubing. Cubing both sides will be very the most appropriate thing to do, because at this level we are facing the problem of the radical root of degree 3. This is our first layer of soil we are face to face while we're excavating, while we're digging now. So we have to cube everything. And then you get 6x squared minus 4x. Oh, it's now in your hand. You actually see it now. But the right side, you see, right side now is experiencing what you've done, which makes 2 become 2 times 2 times 2, right? 8 on top of 1, so just 8. Okay. Now, of course, you could have written it as 2 cubed if it was more useful. But it doesn't look like that would be more useful. That's why it's just like 8. That's the better appearance, I guess, to this situation. Okay, now what? Well, now actually, all you need to do is, well, you see, you can try to find when 3 times x squared minus 4 times x is equal to 8. But do we have any tools, any arsenal of tools, any toolkit with us that helps us to find x values when the whole thing, the whole function of an x equals to something that is not equal to 0? We don't really have that much. We don't have that much, right? Well, everything that all our machinery is given to us. We can use lots of techniques when one of the sides of an equation equals to 0. So it would be great if we can make it equal to 0. That's what you need to do. You need to make sure that eventually one side of your equation equals to 0, because the moment it equals to 0, you're starting your old process all over again. You're starting your not the regular solution. The solution, finding the solution, is now actually appropriate because it means searching for the root. But I have to be careful. We have to put minus. We have to somehow get rid of 8, which means subtracting 8 from both sides. So that will give us 0 on the right side and whatever we have on the left side. And now the left side looks like a new function. It has, yes, it's a parabola in its picture. Yes, it has ABC, and it equals to 0 now. And we're trying now to solve for each root. We create a new function out of nowhere by incorporating both sides. Now it looks like a different parabola, or a different quadratic function at least. And then we have to find the roots. Now, how do we find the roots of the quadratic function? You can complete the square. You can actually, because we're trying to find the roots, we don't want to complete the square. So you don't want to find a vertex form. No vertex form. You don't need that at this point. You're not finding for a vertex. You're not finding for the range.
Right.
Right.
The trinomial, right?
Yeah, you can. So you need to factor. You need to, well, either you need to factor to see the roots hiding inside those factors, or just somehow find the roots right away, or just find the roots somehow. So how do you want to? It's up to you. And in fact, it's not even right. It's not even obvious if they are actually, if we even have any solution. Just because the question was asked doesn't mean that there's an answer. Find the potential roots. Maybe, maybe not. Remember, we are in the real number world. There are certain limitations in the real number world. If we were in a complex number world, yeah, there will be an answer for sure. Okay. So what would you do? Would you like to
factor? So like 2 numbers that add to negative 24 multiply to negative 24 and add to negative 4?
Yes, that would be a representation of the roots with the signs inside the factors. Then you'll have to switch the signs, right? Eventually to get the right roots.
Right.
Or you can switch the signs right before you even do that trick. You can say, yes, they'll have to multiply to minus 24, but they will have to add to minus 4, which is plus 4, if you want to immediately see the roots themselves. Not the way they appear in the factors. The way they appear in the factors is already with the negative sign. That's why. But what they are is not exactly the way they appear in the factor. Because in the factor, when they appear in the factor, before they even appear in the factor, there is already this part that exists there, which is x minus. They are already being anticipated by x minus, right? X minus, this minus part, that's part of a factor. It's part of the structure. It's part of the architecture. It's not part of the entity that will enter the architecture. The entity that enters that architecture is the root value. And it doesn't enter with, it may enter as a negative value, but he will still face the negative value there again. So when he enters the architecture of a factor, he ends up showcasing, appearing as if he had an opposite sign value in front of him. So you have two ways. Either you think about how the appearance of the factors will look like, which is not our question. If our question was to find the factors, yes, what you said would be the best way. Find two numbers that, okay, let me use R1, R2. Find two numbers that multiply to the AC, which is minus 24, and add up to whatever the B is, right? Minus 4?
Right.
Is that what you said? Well, if you actually do that, you're actually not finding the R1, R2. You're actually finding their appearances in the brackets. So you're actually finding minus version of that and minus version of them being multiplied. But because minus versions of them being multiplied still gives you the same answer, minus minus is plus, right? It doesn't matter. It's plus RR or minus RR. It's still going to be plus R1 times R2 multiplication, right? Of two negative numbers doesn't differ from the multiplication of two positive numbers. Minus 2 times minus 2 is not different from 2 times 2. It's the same thing.
Right.
Because even number of times, again, the even power, right? Same thing. Again, you can't have a negative answer when you have an even degree of an exponential. So this negation will become positive thing. So yeah, minus 24, doesn't matter. Yeah, you're lucky, you can say that. But when you say minus 4 as an addition, you mean you're actually negated the addition because you're actually using negative versions of the root values. And you did it because your purpose was to find the factors. Because the question was to factorize, probably fully factorize. So you learn that in school most of the time. But of course, if the question is to find the roots, and you don't care whether you need to find the factor or not, then you can just say, well, it's minus 24 because it doesn't matter. But actually, when I add them themselves, independent of reality in which they will have to settle, themselves, then they will produce actually the opposite value of the B that I see. So it will be the negation of the B, which in this case will be minus 4, which would be plus 4. So, but in another way, you can actually find the magnitudes of those numbers no matter how you think about it. Okay, so do we have any numbers that do that? I don't think so. 6, 4, 8, 3, 8, 3 is 5. 6, 4, 8, 3 is already very close enough, but it's 5 units away. 8 and 3. We probably won't be, maybe, I mean, I kind of don't want to think about it too much. Maybe you can think about it for a second, 10 seconds.
No, 12 and... I don't think it has a solution.
Not the best numbers, right? To think about whole numbers that generate them. Yeah. So at this point, what do you do when you don't want to think like too much, when you already know you kind of reached the limit of how much time you can allocate to that particular attempt? You go to what way? A regular way, maybe? Which way is that?
Where you use the square root. I'm never gonna find
a quadratic formula?
Yes, the discriminant part of it. Just the square root.
What square root? Do you mean the one that incorporates square root? It's one of this particular.
Yeah, b squared minus.
Yes, so which is the quadratic, which is using a quadratic formula, which is the formula that works all the time. So let me just rewrite it. Now, the quadratic formula is something that works all the time. So you can always start by that. Minus 4x minus 8 equals to 0. That's our statement right now. That's the problem we're trying to solve. We transformed our problem from this appearance to that appearance, and then we transformed it from this appearance to this appearance. And now it looks like this. It looks a little bit different from what it used to be. Actually, it looks quite different from what it used to be. So now it's a problem of solving for the zeros, which is a regular, very natural problem for us. And we can always use the formula. And that's why it's called the formula. Use the quadratic formula. If it wasn't the formula, it wouldn't be usable all the time. Well, not all the time, but anytime you want. The quadratic formula. The correct formula exactly that. So you said the correct formula allows you to find those roots by first detecting the middle ground, the position between the two potential x-interceptions, and because a parabola is a perfectly symmetric shape, a geometric shape that has a perfect symmetry, any two locations on that parabola, on two hands of the parabola or branches, will always be equally distant from the middle by definition. It's a symmetric object. But the middle is where the vertex happens. So that's just like you said before. Going from the vertex towards the left, meaning subtracting something from the vertex, and going from the vertex the same amount of distance to the right, meaning adding something on top of vertex, will give you two positions that are equidistant from the vertex. Now, again, because the quadratic formula starts with minus b plus and minus, you know that you are starting from somewhere that is in the middle, because you are now potentially going to reach two equidistant positions on two different sides of something in the middle. It must be in the middle. Otherwise, how can you have equidistant positions? So yeah, so minus b divided by 2a therefore is justified to be the middle of the parabola, which is the vertex's x coordinate, the h in other words, plus minus square root is the part that tells you how far you need to go from the middle. How far? What's the distance? How far do you need to go from the middle in both directions to get yourself to the potential positions where your graph actually lies on the ground, actually touches the ground, gets in touch with the ground, intersects or is intersected by it? Yeah. So, okay, so finding that, I don't want to do it. Now, but this the only thing that you have to know for sure is that, again, since this is a radical, and since you see nothing in its index position, you know it's the 2. You know it's the degree 2, Ayana, which means you know that there is a condition imposed on the potential domain of entries, right, that can be entered. And you should basically expose that and tell yourself that, look, I have 3 potential possibilities in front of my eyes. Either this b squared minus 40 thing ends up going positive. That would be great.
Right.
Of course, it doesn't have to be, right? It might end up being equal to 0.
Sorry, I do.
And that will be all.
In a few minutes, like I have until 12:10 because I have to get to work at 12:30. So
So you tell me when you want. How many minutes do you have?
I have like 5-ish minutes because I need to get ready and then drive.
Maximum. Yeah, I got it. Okay, let's just finish this last thing.
Yeah,
we'll talk about. So 3 things, as you probably remember, right?
Yeah.
I can see that you remember that.
Yeah.
So now, and you remember that we call it a discriminant, D, big letter D. Now, the discriminant word is, of course, it can mean many things, right? But discriminant has, in mathematics, we mean a certain meaning, which is a meaning of differentiating between possibilities, between any number of options, if it's more than one option. We have 3 options, right? Now, these options actually make a huge difference to what will happen. What's the result of b squared minus 4ac being greater than 0? Well, that means that the square root of him, and let me actually, instead of calling him this, just call him d. It means that the square root of him, if he's positive, will be defined, right? Will have an answer because, right, it's okay to have a positive number inside a radical of degree 2. It's perfectly fine. Now, it's also perfectly fine to have a 0 number inside a radical of any degree whatsoever. But the only thing is that when you have this thing equal to 0, then taking a root of it will also give you 0. Right. That means that adding or subtracting means, well, it means that you're not going anywhere, right? You're not going anywhere. You're adding 0 to your vertex, to your center. Where are you going? You're not going anywhere. You're adding 0. Okay, you're not going to the right. And then you're subtracting 0. Okay, you're not going to the left. So where are you? Well, you're exactly where you were in the beginning. Where were you in the beginning? On the vertex. That means there is only one root. And it's the vertex. It means the vertex is exactly on the ground. It either spawns out of it or it comes down into it. Right? Either your parabola is opening, so that's what it is. That means that there's only one real root, one real distinct root, because we can always, in math, we can be fancy with words. We can say, well, it's one distinct real root, but it's actually 2 non-distinct. Right? 2 not different. They're the same. One real distinct root, or what is more important here is that it's actually the vertex. The very, well, I can't say the vertex because vertex is a point. We're talking about an x coordinate. It's the very h of the vertex. Okay, so so we know what h is. No need to. Now, this means one real. This means two distinct roots, right? If you have a positive number inside of a b squared inside of a radicand here, it means that you will be able to add something and subtract something non-zero, something that has some magnitude, non-zero. It's something, which means you will actually go away from the vertex in two directions, equal amount of distance, which means you will find two different distinct locations, which means you will have two distinct real roots, right? Now, what happens when the thing is actually zero, less than zero, negative? Then you run to the same problem. You can't have a negative radicand inside an even degree radical if you're only allowed to use real numbers. We're talking about real numbers only.
Right.
That means there is no real roots whatsoever. Not only distinct, there's none. No real roots. Okay. Only imaginary, fully imaginary roots. Well, actually, they're not going to be fully imaginary. They'll be complex because they'll have the real part, which will be this part, plus something weird, something imaginary, really complex roots. Okay, so can you quickly tell me, in our case, which one of the D's we have, and then we're done at this level, at this point. What was our original function? Remember? What was it?
It ended in 8. It was, I think, 2x squared minus 4x minus 8? 3x.
Yeah, exactly, minus 24. Okay, so what's the D? Can you tell quickly? What's the D?
Or negative.
We need to know the D, right?
Yeah, so it would be 16 minus 4 times 3, which is 12, times C, which is 8. 12.
Minus 8. Minus 8. It's the whole thing. Here it's the whole thing.
Minus 8, right.
Right? A, B, C are actually all of the numbers. A is the totality of the scalarness in front of x squared. B is totality of scalarness in front of x. And C is the whole thing just at the end, in front of x0. Right. Okay, so it's minus 4 squared minus 4 times 3 times minus 8. When you have minus, it means you're adding. And if you're adding something on top of something squared, which is a real number squared, which is a positive number, yeah, you're definitely getting a positive answer, right?
Yeah, it'd be two roots then.
You see? So you only have to think about how many subtractions you have there, right? You have to think about basically how big it is, right? Sometimes you can subtract and you still get a positive answer because this guy is big enough. But in this case, if you're adding, you don't care about what's inside, what's in front. Okay, so D is bigger than 0, which means how many roots we have, therefore? Two real distinct roots. And now you ready to go, right?
Yes.